So discovering electrons led to more questions. And this is what happens in science. You figure out one thing, and that opens up a whole bunch of other opportunities or things to investigate. It's a little bit like climbing a tree. When you come to a fork, you could take one of two different paths. And you take this one, and as you go, you just have all these different things open up in front of you. And so there's really just a limitless number of things that could be investigated. So what were the questions? Well, if there's a negative charge in the electron, a negatively charged particle, there must be something that's positively charged because we know that the atom overall is neutral. So there's got to be something positive in there. How do those opposite charges fit together? Are they stuck together like little magnets? What's going on? Are there more particles in there? Are atoms just a jumble of even more fundamental particles? Are those particles internal solid spheres, or do they have some sort of internal structure as well? That reminds me of the book Horton Hears a Who. Right? So Horton hears a who. He caught this dust speck, and he hears this noise. And Dr. Seuss's imagination, the dust speck is another world with people in it. But they're just really, really tiny. And then you could start wondering, well, what about the dust specks on the dust speck? Is that a world inside of that? How far in could this possibly go? Right? So could these particles, these electrons, could they be composed of smaller particles inside? Lots of questions. Well, Thomson came up with a model. He proposed a model. It's called the plum pudding model. Here in the United States, we're not familiar with plum pudding. So think blueberry muffin. Blueberry muffin, so the electrons are like the blueberries in a blueberry muffin, and this sphere of positive charge is like the muffin part, the cakey part. So you've got these blueberries just kind of irregularly spread throughout the muffin. And that was his idea. I mean, you got to start somewhere, right? Have to talk just a smidge about radioactivity here. It's really covered in Chapter 20 in Chem 1B, but we just have to get a little taste of it. What is radioactivity? It's the emission of small energetic particles from certain unstable nuclei. It was discovered at the end of the 19th century. This discovery allowed scientists to probe the structure of an atom. There's three main types: alpha particles, beta particles, and gamma rays. We're going to talk just briefly about alpha particles. Alpha particles have a positive charge, and of the types of radiation, they are the largest. They're still very, very small. So that's what an alpha particle is. Ernest Rutherford worked under Thomson. So Thomson was his boss. He agreed with Thomson. He's like, yeah, this plum pudding model, this is good. Let's test it because that's what scientists do. So he did an experiment that he thought would confirm the plum pudding model. So Rutherford took positively charged alpha particles, radiation, and directed them at a very, very thin sheet of gold foil. The plum pudding model predicted that those particles would just go straight through the gold foil. So here's the radiation source, the alpha particles. Think of this as a little bit like a pitching machine in baseball or tennis, and it just shoots balls out, right? So the alpha particles are coming at this piece of gold foil, and they expected that they would go straight through. This circle around here is a detector to detect the particles. And so a lot of them went straight through. Some of them got bent a little bit by going through the foil. Some of them basically bounced off the foil. The bouncing off the foil part was very unexpected. Rutherford said that was about as credible, about as believable as if you had fired a 15-inch shell at a piece of tissue paper and it came back and hit you. Can you imagine? A 15-inch shell. That's a big shell. We're talking like bazooka kind of thing, right? I'm not up on firearms, but that's a big shell. You fire that at a piece of tissue paper, what do you expect? Just go blast straight through the tissue paper. No, it comes back and hits you in the face. What? What the heck is going on there, right? That's how these guys felt about the results of this experiment. It's like, well, okay, obviously our model is not right. Something else has to be going on. So they came up with a new model to explain these results, because that's what we do. Here's what was expected. If the plum pudding model was correct, these alpha particles, this is just some charged substance, didn't know what it was, with these little electrons in it. We would expect that the alpha particles go straight through. So they came up with the nuclear model. The nuclear model says that we have a nucleus, very dense matter, and then around that is this cloud of electrons, so mostly empty space, because most of those alpha particles went straight through. So the ones that are just going through the electron cloud go straight through. But the ones that come very close or actually hit the nucleus bounce back. Okay, so maybe think of shooting airsoft pellets at a chain link fence. Most of the pellets are going to go straight through. But if a pellet hits one of the chain link part, it's going to bounce back, right? So that's kind of the idea here. We now know that in the nucleus we have protons and neutrons. Any questions? So building on this idea, Rutherford proposed the nuclear theory. Most of the atom's mass and all of its positive charge are contained in a small core called the nucleus. Most of the volume of the atom is empty space throughout which tiny negatively charged electrons are dispersed. And there are as many negatively charged electrons outside the nucleus as there are positively charged particles inside the nucleus. The atom is electrically neutral. So if you have 5 electrons floating around in that outside part, then you must have 5 protons on the inside. So this model was great, but there were still some issues with it. So they figured out that hydrogen has 1 proton and helium has 2 protons. So if the proton is the massive part of the atom, we would expect that helium would weigh twice as much as hydrogen. It has 2 massive particles to hydrogen's 1. But it actually weighed 4 times as much. Well, look into this, study this. So again, with Rutherford and one of his students, Chadwick, they figured out that that unaccounted for mass was a particle called a neutron. The neutrons are neutral particles that are also inside the nucleus. So now what we've got is we've got protons and neutrons inside the nucleus and little teeny tiny electrons in this cloud around the outside. The neutrons have no electrical charge, they are neutral. So I know there's a lot of terms and a lot of stuff to remember in chemistry, but some of it, I mean, we're not really trying to make it difficult. Look at this. Neutron, neutral. Neutrons are neutral. Protons are positive. Both start with P. Something's negative, that's the electron. The mass of the neutron is similar to the proton. So you can kind of think of them as being very similar to each other, similar in size, similar in mass, but the proton has a positive 1 charge and the neutron has no charge. This explained why the helium atom was 4 times as big. It's got 2 protons and 2 neutrons. It's got 4 massive particles. Hydrogen only has 1 proton. So the mass ratio makes sense. The nucleus is extremely dense, over 99.9% of the mass of the atom, but it occupies very little space. One of the illustrations I saw said that if you took just nuclei from a bunch of atoms and made a ball the size of a period on a printed page, little tiny thing, right? Barely able to see it. It would weigh millions of tons if it was just nuclei. Nuclei are incredibly dense. But the atom itself is not so incredibly dense because most of it's empty space. It's a little bit like a cloud or like fog, right? We're all very familiar with fog around here. You walk through fog. Is there really any resistance? No, you just pass straight through it. You can't walk through walls, but you could walk through fog. Electrons are a lot like water droplets in a cloud or in fog. They're dispersed over a large volume, but they have negligible mass. So very tiny, but they're distributed over this large volume. Clouds and atoms are mostly empty space. Here's another way to think of it. Because if atoms are mostly empty space, why does this desktop seem so solid, right? I mean, you would not want to bang your head on that. That would hurt, right? The variation in density, the non-dense part where the electrons are and the incredibly dense part where the nucleus is, the size differential there is so small we can't perceive it with our eyes. So one way to think of it is to think about some scaffolding, like they put up on the outside of a building when they're doing work. So here, a big scaffolding the size of a football field and 10 stories tall. I think my kids, even my older sons, would think, oh, cool, jungle gym, right? Ginormous jungle gym, let's climb. It's mostly empty space. There's metal bars, but then there's a lot of empty space in between. If you look at it from an airplane, though, flying high overhead, it's going to look solid. As you look through this, you can't see through the scaffolding because the bars are getting in the way, even though it's mostly empty space. Does that make sense? If this football-sized scaffolding was an atom, the nucleus would be the size of a pea, this big, compared to this ginormous scaffolding. So that gives you an idea of the size difference between the nucleus and the atom itself. So when you tap your knuckle on the table, why doesn't it go straight through? It's like taking two ginormous scaffoldings and banging them into each other. Both of them are mostly empty space, but they don't fall into each other. Does that make sense? But then, the scientist thinks, and this is where science fiction is so interesting, well, could we do something to the matter so that we could pass them through each other? I don't know. We haven't done it yet, but it's awfully fun to think about.